I'm happy to introduce Ron Aharoni. So he will be the last speaker today. So Ron, it's a big pleasure for me to introduce you because you was my kind of friend at the Technion. Helped me a lot. And Ron will speak about a rainbow matching through the lens of Drisko's theorem. Initially, it was just a rainbow matching.
Okay.
Actually, it was initially just a rainbow matching, just one line.
Yeah, one rainbow matching, but I thought that was too little for a talk, one rainbow matching. Okay, so first of all, thank you for the invitation, and I'm happy to meet you again, if not in body, then on the internet. I was 2 times in MIPT, I think. No, once. 2 times. Yeah, it was fun. I enjoyed it very much.
And 3 times in Russia.
3 times in Russia. I don't remember. Okay. So this is going to be mostly a survey talk on rainbow matchings. I hope it will contain something new for most of you, but basically it's a survey talk. And there is one theorem that can illustrate all facets, at least those that I'm going to speak today, about of rainbow sets, rainbow matchings. This is a theorem of Drisko from the 80s, I think, 1980s. And it's a very simple theorem. First of all, let me define what is a rainbow set. Rainbow set is one of the most basic notions in mathematics. It's a choice function. It's the image of a choice function. So you have sets V1 up to Vm, and you want to choose points from some of them, but points from distinct ones. So you don't have to choose from, it can be a partial rainbow set. Namely, you don't have to choose a point from each of them, but it's important that you choose a point from distinct VIs. And the VIs we call colors, and that's the origin of the name rainbow sets. And we should be interested, so here is the precise definition. So you have these sets V1 up to Vm, and you want Vi1, Vi2 up to Vik, that's vertices chosen, each from a different Vij, the set Vij. Okay, and we shall be interested mostly in not general rainbow sets, but the sets are going to be sets of edges of graphs usually, but sometimes also hypergraphs. And we should require that the image, the edges that you choose in the rainbow set are disjoint, okay, which means that you get a matching. And here is the theorem that I'm going to talk about. It's Drisko's theorem. I wrote here Drisko and also myself and Berger, because the original theorem was a bit restricted. It was about Latin rectangles, and the general formulation is what you see here.
Sorry, what is a rainbow matching? What is
rainbow matching? So again, you have sets V1, capital V2, and so forth, and they are all sets of edges in something, in a graph usually. We'll mostly see graphs. So you'll have sets of edges in graphs. And you want to choose one from each, at most one from each, so as to get a matching. So you want to choose disjoint, guys. Disjoint edges. Okay. So
someone is asking in the chat, Ron. Someone is asking in the chat. Their VIs must be disjoint.
No. I drew them disjoint just for convenience. They definitely do not have to be disjoint.
So this set of edges,
they can be identical if you want.
Okay.
You can take identical ones if you wish. Okay, but no, they are not disjoint in general.
So there are no constraints.
No constraints on the VIs. Okay. And the theorem is this. Suppose that your sets VI are matchings, each a matching of size n. Okay. And suppose that you have many of them. How many? 2n minus 1, that's the number. You have 2n minus 1 matchings, each of size n. Then you have a rainbow matching of size n. Okay. That's the theorem.
Is there any restriction on the number of vertices here, or
No restriction. No, and in a bipartite graph, I wrote here in a bipartite graph. We'll also get to non-bipartite, but for this time being, it's bipartite graphs. Okay. So let me show you sharpness. Why is it sharp? So this will give you some gist of some feeling for the gist of the theorem. So take n equals 4, and look at this cycle, an 8 long cycle of length 8, and take the red guys, the red edges, 3 times, and the blue edges again 3 times. So you get together 6 matchings of size 4, and they do not have a rainbow matching of size 4. Why is that? Because how does a matching of size 4 look like? It's either the blue guys or the red guys. There is no other matching of size 4 in this picture. Okay. So if it's the red guys, you do not have 4 edges to represent them. You have 4 sets to represent them, 4 matchings. You have only 3 matchings that are red and 3 matchings that are blue. So you cannot choose 4 red edges in your rainbow matching. So you're not going to be, you're not going to have the red matching, and you're not going to have the blue matching. Okay, I hope this gives you some feeling of what is the point in this theorem. And actually, this is the only example, I mean, for generalize it to general n, this is the only example where 2n minus 2, this is the number that you have, twice n minus 1, 2n minus 2 do not suffice. Usually 2n minus 2 suffice unless you're in this precise picture. Okay.
x3, red matching x3. What is x3?
And now times 3.
Times,
you take the red matching,
red matching
and multiply it 3 times. You take the blue matching and multiply it 3 times.
What is multiplying of matching?
You take copies. We said that they don't have to be disjoint, right? They can be the same. So you take 3 times the red matching, 3 times the blue matching, so you have altogether 6 matchings of size 4, and it doesn't suffice. So 2n minus 2 do not suffice.
Thank you.
So this is the theorem, and it has many proofs. It made me think of when does a theorem have many proofs, and I think, but anybody can venture his own or her own opinion, I think it happens when the theorem is not deep, so you can have many proofs, easy proofs, but it is somehow significant. It sits in a rich corner of the theory. And I think this is the case here. It's not deep, not at all deep, a deep theorem, and give you a proof. So it has actually 2 totally different topological proofs. I'll show you one of them. And it has at least 2 combinatorial proofs. I'll show you one of the, definitely the simplest proof. And the simplest proof goes by going lower, to a lower level. Instead of looking at matchings, you look at paths. So you have a network. What is a network? It's a digraph with 2 distinguished vertices, namely S, which is source, and T, which is target. And we are looking at ST paths, okay? And suppose, let me close the window so that the dog does not express her opinion of this talk. Okay, so suppose that you have n vertices, inner vertices. So you don't look at S and T, just the other vertices. Suppose there are n vertices in the middle, and suppose that you have n plus 1 paths from S to T. The theorem says, the lemma says that there is a rainbow path from S to T. Okay, and this is sharp. Suppose n paths do not suffice, because if you look, well, let me skip that. This is sharp, definitely sharp. So here's the proof. Take a maximal rainbow tree, rooted at S. Okay. So what is a rainbow tree? Tree consisting of edges from distinct paths. So you have a system of n plus 1 paths, And suppose that you can choose the maximal tree of this rainbow is obtained by choosing an edge from some of them, but distinct ones. And you take a maximal one. Okay. If this contains T, this tree, then you have a path from S to T, which is rainbow from different paths. If not, then since the number of vertices in the middle is n, the number of paths you have used is no more than n. And we know that there are n plus 1 paths. So one of them hasn't been used. So here it is. There is a path that you haven't used. It must leave the tree at some point. In order to get from S to T, it must leave the tree. So what you do is you take the first edge that leaves the tree, here it is, and you get another tree which is larger, contradicting the assumption that the tree that you chose was maximal. Okay, not very hard. Okay, now let's use this to prove Drisko's theorem. So you look at a maximal rainbow matching. Suppose that the maximal size of such a rainbow matching is some number m, which is smaller than n, strictly smaller than n. Remember, we had 2n minus 1, you probably forgot, but let me remind you, Drisko's theorem speaks about 2n minus 1 matchings of size n. So you've used less than n, then you're left with more than n, which is larger than m, so you have more paths, more matchings that you haven't used than edges in the maximal size. So in the red guy here, the red matching here is the maximal size rainbow matching. And every matching unused is of size n, which is larger than n minus 1. So it has, I think you know that, it has an improving, augmenting path, alternating path. From now, you have to choose to define what is S and T. S represents all vertices outside the red matching inside A, and T represents all vertices outside the red matching in the other side. Okay, and every matching, each of the at least n matchings that you haven't used gives you an augmenting alternating path, which is a path from this S to T. And think of the red edges as vertices. So if you think of them as just vertices, you contract them to be vertices, then this blue guy here is a path from S to T. So as we said, there are at least n paths from S to T, and the number of red vertices is just n minus 1. That was our assumption, that, or at least less than n. Assumption that the maximal rainbow matching is less than n. So the lemma that we just proved before says that there is a rainbow alternating path from S to T. So apply it. If you've done any course in matching theory, you know what is to apply an augmenting path and augmenting alternating path. It means taking the odd edges in and the even edges out, or the red edges you take out. And what happens? So you take this red matching and add the blue, the yellow, the green, and the purple edges. You put them in and throw the three edges that you touched, and you get one larger matching that is a rainbow, called alternating path, that you used a rainbow and you used only unused colors, unused paths. Okay, at least you could feel that this, if you didn't follow all the details, it's a late hour, you could feel that, well, this is not a deep theorem. Okay, there is an alternating path.
Ron, sorry for interruption. Who is the author of this proof, and where is it?
I think it's mine, but it doesn't matter. I mean, it's probably not very far from the original proof of Drisko.
It's very similar to the Drisko's proof.
I think so. We also use alternating path.
And it also recalls me the proof about odd cycles.
Yeah, it's I'm not going to mention it today, but I will not have time. Okay. Yeah. It's all not very hard stuff. Okay. So first of all, I told you that I think it sits in a rich corner of the theory. So let me show you it by, first of all, giving you a stronger generalization, which I like very much for two reasons. So first of all, let me state it. What's the theorem? In the theorem, you have 2n-1 matchings, each of size n. N. Suppose that you take the first n and replace them by a matching of size 1, matching of size 2, matching of size 3, up to n. Okay? So this, I wrote it in a formula, and again, it's past 8 in the evening, so I'm not sure how awake you are to follow a formula, but the sizes of the matchings are mi is at least the minimum of I and n. So the first matching is of size 1, second matching of size 2, and as from n, the matchings are for size n. And this suffices, meaning this must have a rainbow matching of size n. Why do I like this theorem? For two reasons. One is it has only a topological proof. I don't know any combinatorial proof for this. And non-trivial proof, the other proof that you will see, topological proof of Drisko, is easy. This is not so easy. And the second is that it's applicable. We'll see it in application. Okay. Okay. Now here's a conjecture. This is the most tantalizing. There are two tantalizing conjectures here. The first concerns matchings in general graphs. So in a bipartite graph, 2n-1 matchings suffice to have a rainbow matching of size n. In general graphs, it's not true, but we strongly believe, that 2n matchings suffice. There is a very strong reason to believe it. I'll tell you it in a minute. But again, 2n matchings in general, and we are very far from proving that. So the best we know is 3n-3 matchings, and this is really hard work, not very rewarding. You get 3n-1 is, I think it's easy. 3n-2 was a result with Chudnovsky and Seymour and Eli Berger and Howard. And this was also not so easy. And 3n-3 is working hard to get not much.
What is true fractionally with some additional conditions?
Okay, I skipped that. I'll explain it. So the theorem says that it's true fractionally, which means the following, that you have 2n matchings of size n. You can choose an edge in each, okay, so that the fractional matching, the fractional matching number of what you get. So again, you choose an edge from each of them, so you get a graph. And this graph has a large fractional matching number, namely its new star, as you know, if you know this notation, is n, at least n. Okay, so that's what it means, that it's fractional. And again, the proof for that is topological, and I'll mention about it something soon. Okay, let me just show the sharpness, why 2n-1 do not suffice. So n equals 2, take n equals 2, so 2n-1 is 3, and we are claiming that this is not sufficient, you need 2n. Take this blue, red, and green matchings, 3 matchings of size 2, and as you see, each green meets each blue and red, so you cannot take, and each red meets each blue, so you cannot take a matching of size 2 of different colors. So there is no rainbow matching of size 2. You can generalize this construction to any even n, and the conjecture is that for n odd, 2n-1 suffice. Okay, but we are really very far from proving that. And let me mention the really tantalizing conjecture here, which is the following. So remember, Drisko says that 2n-1 matchings suffice to have a rainbow matching of size n. 2n-1 matchings of size n suffice for n. Suppose you only need n-1. The conjecture is that you can drop it to n matchings of size n. This is not going to be a very easy conjecture to prove because it implies very well-known theorem conjectures from the 70s of Reiser and others. And so it's not going to be very easy. And okay, sharpness here is easy. So take again the same picture and take again n equals 4 just for the example, and look at the red matching 3 times, the blue matching 1 time, so you have 4 matchings, and as we saw before, it doesn't have a rainbow matching of size 4, it only has a rainbow matching of size 3, so that's easy. And now let me return to this conjecture about general graphs. It would follow from a generalization of the other conjecture, so the conjecture of myself and Elibert, that n matchings of size n in any graph. So before we mentioned bipartite graphs, n matchings of size n in any graph have a rainbow matching of size n minus 1. Why does this conjecture imply the previous one about matchings, 2n matchings of size n having a rainbow matching of size n in any graph? Because, so you have 2n matchings, remember? That's the conjecture, 2n matchings of size n. Take each of them and duplicate to make 2 copies of your vertex set and duplicate double every matching. So the matchings were of size n. Now double them, so each matching now becomes a matching of size 2n. Okay, n in one copy of your vertex set, n in the other. Okay, so you now have 2n matchings of size 2n. Now, the conjecture of Elibert and myself is that if you have 2n matchings of size 2n, then you have a matching of size 2n minus 1, rainbow matching of size 2n minus 1. Now, if you remember, it lives in 2 copies of your graph. So you have 2n minus 1 edges in the rainbow matching, living in 2 copies. So by pigeonhole, one of them is of size n, which is what you wanted. So the second conjecture, the conjecture generalizing, say, Reiser's conjecture, implies the 2n conjecture for general graphs. And if you work on you see that the obstacles are the same, are very similar. So I do think these 2 conjectures are closely related, and which is said, I mean, it means that even the 2n conjecture for general graphs is not going to be easy. I think so. Okay, so let me skip that. Let me just mention a very beautiful theorem. I like it very much, this theorem of Correa, Sodakov, and Tomon, about matchings in R uniform hypergraphs. So it says that the following, that T minus 1, we don't know their exact precise results, but this is the best asymptotic results known so far. If you have T minus 1 times RT, choose R, plus 1 matchings of size T in an R uniform hypergraph, then you have a rainbow matching of size T. And why do I like so much this theorem? Because it's proof. It's very beautiful, and it uses multilinear algebra, which I have been dreaming all the time to use in this context. And I wasn't able to do anything using multilinear algebra, but this is a very beautiful application of multilinear algebra. Okay, let me mention a bit about topology. So topology is the theory, algebraic topology, is the theory of holes. And there are 2 basic definitions, 2 basic parameters there of a simplicial complex. Now, what is a simplicial complex? Think of it just as a topological space, okay? Any topological space. So what is eta? Eta is the minimal dimension of a hole. So let me just give you an example. Here is a simplicial complex. So think of this guy, this house, empty house, just as a topological space. And if you see, it has in the middle a hole of dimension 2, right? The square is, the hole is of dimension 2. So eta is 2. There is no smaller dimension hole. Here there is no hole at all, so eta is defined as infinity. And here there is a dimension 2 hole, if you see in the right triangle, but there is a smaller hole. What is a smaller hole? Here it is. you see these 2 points form a hole, namely the edge between them is not filled in any way. Okay, so this has a hole of dimension 1. So eta is 1 just means that you're disconnected. The space is disconnected. Okay. Now there is a dual notion, and I don't know if you see it because what should I do now? Because in the top there is something that covers for me. I think it covers also for you, right? Okay, so let me just tell you. Lambda of C, lambda is for array, is the largest dimension of a whole.
We see this definition.
Sorry?
We see this definition.
You see, I don't see it because it's covered in my, okay. So the largest dimension of a whole. So look again at this picture in the 2 triangles. So if you remember, eta was 1 because there was a hole of dimension 1, but there is a larger hole, the right rectangle, the right triangle is of dimension 2. So lambda is 2. Okay. Now there is a connection between the two. There is something called the Alexander dual of a complex. Now you really need to use complexes. Complexes are formed from convex simplices. And the dual of a complex is something funny. You take twice the complement, which is funny because you don't go back to the original one, because there are 2 complements. First of all, you can take all simplices that are not in your complex, and then you can complement each of them. Take the complement of each of them. This is how you form the dual. We're not going to use it, don't worry. So if you didn't get precisely what it is, but it connects eta with lambda. Eta of the dual is v minus lambda of v minus lambda minus 1 of the Alexander dual. So you can work with one of them, with either the eta or the array, as you wish, by just passing from a complex to its dual. Well, there are 2 basic theorems, which I don't know if I want this late hour. But okay, let me just mention them. So there is a theorem of myself and Berger, which is related to topological hole, or a matroidal version of topological hole. And there is a Kalayim-Shulam theorem, which is a matroidal theorem also. They are the same theorem. These 2 that you see here are the same theorem, so it's hard to follow each of them. I'll read them in a minute. But they are the same theorem by going to the dual. One speaks about eta and one thing speaks about lambda. So the theorem with Eli Berger is that in both you have a matroid and a complex, matroid M and complex C on the same vertex set. And what you want to get is in the, my theorem with Berger is a base of M that belongs to the complex. Base of M means it's big, belongs to the complex. The complex contains small sets, it's closed down. So you want big in one sense and small in one sense. And the sufficient condition for this is that eta of any set in the complex is at least the rank of the matroid in the restricted, not contracted to S. Okay, if you don't know what it is, forget it. We're not going to use it. I'm just going to tell you that there is some theorem of that sort, and we will get a better case, a simple case of this in a minute. Now, the theorem of Kalayim-Shulam is even harder to get, but what you're looking for there is a set belonging to the matroid and not belonging to C. Belonging to the matroid means it is small. The matroid is closed down. And not belonging to C means it's belonging to the complement of C. Complement of C is filtered, closed down. So you want something that is small in one sense and big in the other. The same flavor as the top one, and forget the. I'm not going to define what is link here, but it's again if lambda is less than rank, and in the theorem of With Berger, it's eta larger than rank. So you can have a feel that they are the same theorem if you go to the dual. Okay, it's just to give you some flavor, because we're going to restrict ourselves to a special case when the matrices are partition matrices. And if you apply the theorem with Berger to partition matrices, you get topological whole, which is the following. If you have sets V1 up to Vm, and eta of any union of k of them, k is not mentioned, it's I there, and eta of the union of any k of them is at least k, then you get a rainbow set for these sets V1 up to Vm belonging to the complex. Let me just mention, perhaps some of you know Rado's theorem, which is the matrixal version of Hall's theorem. This is just the same flavor, okay, in its generalization of Rado's theorem. Okay, and the Kalayem-Shulam theorem is even simpler. This is what I'll need. So forget the previous, I mean, you don't have to forget, but don't worry if you didn't get much of the previous one. This is better. Here, this is more important, because this we are going to use. It says the following. So if you apply the Kalayem-Shulam theorem to partition matrix, you get the following theorem. If for every set S, a lambda of this set S in the complex is less than M, then any M plus 1 sets not in the complex, namely they are big, have a rainbow set again not in the complex. Oh, it's really late to digest such a theorem so quickly, but let me just say again. If lambda is less than M, it's a strong condition. Lambda big is easy. Lambda small is gives you some information, because lambda is the maximal size of a hole. So it means all holes are less than M. Then if you have M plus 1 sets that are big is not in the complex, they have a rainbow set that is big. It's this theorem. But we are going to use them for the following thing. Let's B is B for bipartite, M is for matchings, N, BMN is the set of bipartite graphs with matching number smaller than N. No matching of size N. It's a complex, it's closed down. If you take a subset of edges satisfying this, then it also satisfies it. It doesn't have a matching of size N. Now, if you know something about the Lorraine number of this thing, then you're going to get a rainbow version, a rainbow theorem somehow by the Kalayem-Shulam theorem. So here's what we proved. We know that what is the lambda? Lambda is 2n minus 2. And now you'll have to exert your memory and remember, Kalayem-Shulam theorem says if you have one more set than this lambda, if you have one more set that do not belong to the complex, what is not belong to complex contains a matching of size n. If you have one more is 2n minus 1. 2n minus 1 sets containing a matching of size n, namely it's not in the complex. So 2n minus 1 matching of size n have a rainbow matching of size n, namely a set not belonging to this Drisko. Okay, so this theorem together with Kalayem-Shulam gives you Drisko. So this is one topological proof. That's the easy topological proof. It gives less than the other topological proof which uses Hall's theorem. Okay, I don't know if I want to go. I mean, it's really late, and I don't even know how much time left. Okay, I have some time left. So, Sung-Hoon Lee, who is a student of, so it's really late, I forget, the Korean guy with the, I'm really ashamed. Do you remember the Korean guy with Holmsen? Yes, sorry. So Sung-Hoon Lee is a student of Holmsen, and he found what is lambda of non-bipartite MN. What is this? Non-bipartite MN is the complex of sets of edges in any graph, not containing a matching of size n, And he found that the lambda is 3n minus 3. So let's practice Kalai-Mishulam again. What does Kalai-Mishulam say? If you have one more set, so 3n minus 2, 3n minus 2 sets that do not belong to Mn. What does do not belong to Mn? They contain a matching of size n. So 3n minus 2 matching of size n have a rainbow matching of size n, namely a rainbow set not belonging to the complex, namely not having a matching of size n. So this we prove this in a non-topological way, but topological proofs have an advantage, which is hard to explain, but the advantage is that they have cooperative versions. What is cooperative? You don't need that each matching will be of size n. It's enough that every two of them together are of size n. There is a theorem of Pach and Holmes and another guy that I forget that is of this flavor. So again, what Sung-Hoon Lee proved, that if you have 3n minus 2 sets of edges, that every two of them contain a matching of size n, that suffices to have a rainbow matching of size n. So topology has its advantages. Okay. Let me just mention something really simple, which let's go back to networks. So take a network with source S and sink T, and look at the complex of sets of edges not containing an ST path. You see, complex is a set of sets that is closed down. A subset of something in the complex should be in the complex. So the sets of edges containing an ST path is not a complex. It's a filter. It's closed up. But I want something that's closed down. So I'm looking at the complex of sets of edges not containing an ST path. Okay. And here is an easy theorem that if you look, let n be the number of inner vertices, then lambda of this complex that you mentioned, the Leray number, if you remember, the largest dimension of a whole is n. That's not hard. Let's practice again Kalai-Mishulam. What does it say? That if you have one more set, namely n plus 1, lambda is n. Let's just practice. If you have one more, namely n plus 1, sets not belonging to the complex. What does it mean, not belonging to the complex? It means they do have a path from S to T, containing path from S to T, have a rainbow set not in the complex, namely containing a path from S to T. That's the lemma that we had before. If you remember, if you have n inner vertices, then n plus 1 paths from S to T have a rainbow path from S to T. We even proved it. That's a simple proof with the maximal rainbow tree. Okay, so that's the corollary that we said before, and that's fine. Now let me just mention a recent result with this is, let me see, yeah, with Joe Briggs. So here is a theorem that generalizes both Drisko and the last corollary, the last lemma that we mentioned. So here it is. So we have the parameter P, we have two parameters P and N. And suppose that you have 2P plus N minus 1 sets of vertex disjoint ST paths, each consisting of P paths. If you have that, don't worry, I'll give you examples that will simplify things. But the theorem is that if you have that, so you have families of P paths from S to T. And you have how many of them? 2P plus N minus 1. Then you have a rainbow set of matching edges that contains a P disjoint ST paths, a family of P disjoint ST paths. Now, I'm sure you didn't get it, what it says, but let me give you two examples, and then it will make things easier to digest. Put n equals 0. So no inner vertices, just the set S and the set T. Okay, you can have sets of sources and things, S and T. And suppose your n is 0. What does it mean? No inner vertices. What does it mean, no inner vertices? It means a bipartite graph. So you have, if you put n equals 0, and you have 2p minus 1 sets of disjoint ST paths, that's matchings, right? If you don't have inner vertices, then a path, the ST paths are just edges. And they are disjoint, so this is a matching. So you get Drisko. You have 2p minus 1 sets of vertex disjoint ST paths, each consisting of p paths, so 2p minus 1 matchings of size p. You have a rainbow matching of size p. That's Drisko. Put now p equals 1. What does it mean p equals 1? P is the size of the sets of edges. So what does it mean? Each set is a singleton, p equals 1. So you have, and any, if you put in the theorem, so you get 2 times p is 1, so 2 plus n minus 1, so it's n plus 1. If you have n plus 1 paths, because each set is of size 1, so it's just a path, you have n plus 1 paths between S and T. There is a rainbow path between S and T. That's the lemma that we repeated a few times and we started with.
Sorry, what is n in this theorem? N.
Right. You're right. You are. N is the no general. No. General. Any n. Take any numbers. P and n.
Any number?
Any numbers. Pick a number. Any number. 2p plus n minus 1 sets. So it's good for any number. Okay. So I don't think it's a really breakthrough theorem, but the two things about it, it generalizes two facts that seem to be far apart. So it generalizes both. And the only proof that I know for it, we know for it, uses one of the versions of Drisko's theorem, the 1, 2, 3, n, if you remember, that can only prove who is currently proved only using topology. So again, I like results that do not have combinatorial proofs. So this one so far doesn't have one; it has only topological proof. So that's why I personally like it, although perhaps it's not a fundamental one. I think that's it. Yes.
And n is not connected in any way to this structure, so you can take.
No. It's general.
Oh.
Okay. You see, I can put your n equals 0.
It's impossible.
Yeah.
The theorem, let p equal to 1, then any n plus 1 sets, and
any n plus 1 paths from S to T have a rainbow path from S to T.
P paths have a rainbow.
No, if P is 1, it's just one path. Okay.
And arbitrary. Okay.
Okay, so it's very general indeed. So, and I like usually challenging people to give combinatorial proofs for theorems that I know how to prove topologically. Usually, it's hard. I mean, often a topological proof cannot be replaced. Not knowing, we don't know. So for this, we don't know it when we are.
Okay, thank you, Ron.
Okay.
So, do you have questions?
What is the cardinality of set S and T in this?
Any. So these are sets of sources and things. So all edges, there are no edges going into S, you can assume that. No edges going out of T, you can assume that. But I'm not sure you mean to assume that. I think you don't. It's just sources.
In between. So did you say that this has a topological proof but not combinatorial?
I don't know a combinatorial proof yet. So which is fun. I mean, it's usually a challenge. I sometimes give my students such results, but that I can prove topologically, and it never, none of them is ever given a topological combinatorial proof.
Okay.
So, yeah.
Maybe if you would like, could you share any kindergarten problem in this family of in this infinite family of problems, Drisko type problems? Is there any that you can share?
The paper is going to appear. I mean, you don't mean really kindergarten. You mean nice problems. So the paper is going to be on the archive soon, and it contains many problems. So you will be able to look there. Okay, I don't remember offhand.
Okay, good. Thank you.
Here is one very strange phenomenon. We looked at sets of edges, sets of matchings of size 1, 2, 3, 4, up to n. There is a theorem that I mentioned. It's 1, 2, 3, n, and then n, 2n minus 1. That suffices for n. Now, how much?
It was in the beginning, the one of the first.
Yes, but suppose you stop after n steps. So you have 1, 2, 3, up to n. How large a rainbow matching can you find? So my guess would be half n, 2/3 n, I don't know. The computer says n minus 2. So in all examples that we know it's n, but probably it's just the law of small numbers.
So initially we have n matchings and they are of size 1, 2, 3, up to n, yes?
Yes, yes.
And
how much, what's the size of a rainbow matching that is guaranteed?
Of course, n over 2 is guaranteed.
N over 2 is guaranteed, yes. But
the
computer experiments say n minus 2. Now, perhaps it's the law of small numbers, namely for small numbers it's n minus 2, perhaps it's n minus 2 log n or something, or even n minus half square root of n or something like that. But we don't know. This is open.
Okay. Thank you. Thank you.
Okay.
It was interesting. Thank you, Ron.
Thank you.
One more question, Ron. So, what about the non-reachability complex? I mean, what is the topology of that? What is the topology of non-reachability complex?
Can anybody repeat what it says?
What is the topology of non-reachability complex that you defined?
Is the non-reachable. The non-reachable is just, you understand what it is? It's the set of edges. I don't know precisely. You mean what is the, how does it look?
Yeah, what is the homotopy type? Is it
I mean, spheres of size, it's probably bouquets of spheres of size n plus n. Oh, dimension n, something like that. But I'm really, I'm just guessing. It's interesting. But you see, there is a book of some Swedish guy, whose name I forget, that defines all possible all complexes that you think of, that you make of graphs. And he finds the real topology, namely how they look. So perhaps it contains something like that. It contains this complex, perhaps. It's a really fantastic book. It's called Graph Complexes.
The name of the book? Oh,
Graph Complexes. And the name of the author, I forget. It's a Swedish guy, a student of. Oh, it's a late hour. That is the famous Swedish topologist. Yes, yes.
Björner or Kozil?
Yes, Björner, student of Björner.
Thank you.
Okay.
Okay, thank you, Ron. Thank you.
Thank you for listening. Bye.
Okay. Okay, it seems it's the last talk.
Yeah, thank you for organizing. Let's clap for Sasha. I think that's a good idea, no?
Thank you.